Hi guys. Okay, so let's finish this chapter 11 on acids and bases. And here in this video, we are going to do the directions of the reactions, which is the direction of equilibrium. And then we're looking the dissociation constant of the acids and bases, and then the dissociation of water, and then calculating the OH ions and the hydronium ion concentrations, then the pH scale. Now, there are certain things that you're going to leave out because the thing is that they involve the using of calculators with the log functions. And I'm not sure how many students are comfortable with doing that. Every calculator has its own, a way of doing these calculations. And the book and the handout, although tells you, what keys to punch in order to do that. But since it's an asynchronous class, and I think it's better that we get rid of this calculations, although they are fairly simple, but, so for that, you leave out those calculations where the log keys need to be used on the calculator. And these are the calculations shown on page 419, 420, and 421. And similar calculations are also with the buffers. So I'll walk you through the buffers, I'll explain you what the buffers are, but when it comes to calculations using the buffers, in those we're not doing those. So you're going to leave these out, but you're welcome to, advanced learners are welcome to, work on their own if they want to. But I'm not going to cover anything from this on the exam. So just keep that in mind. Okay, so let's see. And then the important things are obviously, the titration is very important. Okay, so this is going to be on the test, that is for sure. Okay, this is definitely going to be on the test, the titration. And, the directions of the reactions of acids and bases, all these other things are also important. But definitely titration is going to be on the test. Okay, so first of all, before we do these proton transfer reactions in the directions of the equilibrium, let us first of all review the conjugate acid base pairing, which we had already covered in the previous, lecture video, but I just want to review this again. So remember that every acid has a conjugate base, conjugate base, and the difference is of one hydrogen ion. So acid is going to release one hydrogen ion, and it's going to give the conjugate base, which is Cb, which is one less hydrogen ion. And anytime, a plus charge is gone or removed, then generally a negative charge appears. Negative charge appears because it has, you have gotten rid of the hydrogen ions. So look at this here, H3PO4, okay, H3PO4. This is the acid because hydrogen is in front. So we already discussed that. Hydrogen written in front. So that's the acid, okay? So when it gets rid of only one hydrogen ion, then it will give you H2, right? PO4. And now one hydrogen is gone, so it leaves you with one negative charge. Okay, so this is the conjugate base of H3PO4. Clear? Now, let's look at this H2PO4 with one negative charge. Hydrogen is still in front. So therefore, this is going to be acidic in nature. Okay, this is not 100% acid, but it is that nature is acid. Now, it gets rid of one hydrogen ion. So if it got rid of one hydrogen ion, one more negative charge appears. So now we have HPO4 with two negative charges. Here was one negative charge. So this is the conjugate base of H2PO4, one negative. Okay, now let's look at this HPO4 with two negatives. Okay, and it doesn't matter whether you write -2 or 2-, it's the same. This is again acidic in nature. minus one hydrogen ion, and this gives you PO4, and now one more negative charge comes. So it's -3. And this is the conjugate base of HPO4 -2. Okay, so this is how, this is the conjugate acid base pairing comes in. So that is as related to the acids. So this is the situation with the acid. Now, acids will give you a conjugate base. Okay, now let's look at the base. Every base will have a conjugate acid. And again, the difference is of one hydrogen ion. So here's the base. The thing with the base is it will accept the proton. So it adds one hydrogen ion and it makes the conjugate acid. So Ca is the conjugate acid of whatever the base is. Like for example here, you have let's do this one, NH3, ammonia, NH3, okay? Ammonia is acting as a base because ammonia has these two lone pairs. It gives those lone pairs. So it's a base, electrons. Now, when it adds one more hydrogen ion, then it becomes NH4 with a positive charge. So this is conjugate acid, sorry. So this becomes the conjugate acid of NH3. Okay. So in this case, whenever a proton is being added, a positive charge comes or it is neutralized, either way. So let's look at this another one. H2O, water can act as an acid and a base. So in this case, water is acting as a base because water has these lone pairs. Anytime there are lone pairs, then they are going to, they can be given, okay? Why am I getting these notifications once again? Okay. Now we have H. It adds one more hydrogen ion. Okay, so this becomes H3O plus one charge. Okay, and so this is plus one charge, plus one charge. This is the conjugate acid of H2O. Okay, now let's look at another one. For example, H. So let's look at this one. P, or let me do this here. Cl minus. This is a chloride ion. Remember, all the bases are going to have like electron rich in some way, either a negative charge or lone pairs, right? So that's going to be a base. So base is anything that has a negative charge or or lone pairs, lone pair of electrons, lone pair of electrons. Okay, so that's going to be a base. Now, so whenever a base comes, then like I said, that the negative charge is neutralized when a positive hydrogen ion is added. Okay, neutralized or a positive charge appears. So as you can see that, here a positive charge has come when a hydrogen ion is added to a neutral molecule. A positive charge comes when a hydrogen ion is added to the neutral molecule. Now in this case, there is a negative charge. So that is going to get neutralized. So this becomes HCl. When a hydrogen ion is added, then this becomes the conjugate acid of chloride ions. Okay, so did I write this here? Acid is a negative charge appears. Yeah, negative charge appears when hydrogen ion is removed. Okay, here charge neutralized, negative charge or lone pair on electrons makes a base. When hydrogen ion is added, negative charge neutralized or a positive charge appears. Okay, so that's the conjugate acids. Okay, so let's put this here. So this is the HCl. All right, same is the case if you have like SOH. Let's do this here. HSO4, 1 negative. So this is again a negative charge. So this is going to be neutralized. So when you add 1 hydrogen ion, then it becomes H2SO4. Now, this is acting as a base because of the negative charge. Okay, so this is the conjugate acid of HSO4, 1 negative. Okay, now, so this is the basic thing. Now let's just do one study check problem here. Study check. 11.3, page 405. Page 405. Now what do you see here? Here we see that HCN is aqueous. Okay, HCN is aqueous plus sulfate ion, SO4, 2 negatives at the equilibrium, and they are given the CN minus, aqueous, and this is also aqueous, and that gives you HSO4, 1 negative, aqueous. Okay, so now the question is identify the conjugate acid base pairs. So remember that every base will have a conjugate acid and every acid will have a conjugate base. Now, excuse me, now pay attention to this, that first always, here's the thing, first identify the acid. Generally, you know, we can determine the acids. How do you know? First identify the acid, because then the other one would be a base. So the acid is hydrogen is written in front. Either it is going to be an acid or it will be conjugate acid. Okay, so in this case, and generally acids would be hydrogen is written in front, and generally they would be neutral molecule. Then everything else falls in place. So if you look at HCN, so here we see that HCN is acting as an acid. HCN is the acid. Let me write this in another color, as an acid. So that's what we identify. So remember, every acid will have a conjugate base. So here, this gets rid of 1 hydrogen ion, and what is left now? CN minus. So this is the conjugate base of HCN. Okay, so this is the acid, this is the conjugate. So these two are related, in other words. Next is obviously, now we have the sulfate, SO4, with 2 negatives. Remember that anytime there are too many negative charges, negative charge or the lone pair, this is very important. Negative charge or the lone pair of electrons is what makes in something a base. Okay, an acid, I hope I wrote this here. Acids will have the hydrogen is always written in front. I think I will, hydrogen is written in front for the acids. Okay, so keep that in mind. And for the base, the charge and the lone pair, charge always a negative charge or a lone pair. So either way, neutral molecule. So here we have the negative charge. So obviously, and there is no hydrogen written in front. So this is obviously a base. So this is a base. And this base is, now here we have every base will have a conjugate acid. So that means this hydrogen that is released by the HCN is being absorbed by the sulfate ion. Okay, so this becomes HSO4, 1 negative. Remember, anytime one hydrogen ion comes, it neutralizes one negative charge. So here we have, this is this. So this becomes conjugate acid of SO4, 2 negative. Okay, so this is very important that, you identify these pairs. Okay, so now comes the strengths of the acids. Now, very important is the strengths, STRENGTHS, strengths of acids and base. And we are going to use the table in the handout. Okay, so here you will use table 11.3. Okay, this is the relative strengths of the acids and bases, and this is also in your handout. This is also in your handout. Now, where? In your handout, you will see this table we are talking about. You see that? In your handout, you will see this table. And this is on page, I believe, page 15 or 16 or somewhere in that, yeah, 15, on page 16, okay? Now, look at this table very carefully. 11.3. Now, what do you see here in this table? On one side are the acids. The other side is the conjugate base. This side is the acid, left side, right? And this side is the conjugate base. Clear? So every acid will have a conjugate base. So as you can see, hydroiodic acid, -1 hydrogen. So I'm just going to put it here. The hydrogen ion, the iodide ion is the conjugate base. Same is the case, hydrobromic acid, HBr. So the bromide ion is a conjugate base. Perchloric acid, -1 hydrogen ions, leaves you with the perchlorate anion. That is the conjugate base. HCl, the conjugate base is chloride ion. H2SO4, conjugate base is HSO4. HNO3, oh sorry, this is, yeah, nitric acid. HNO3, the conjugate base is the nitrate ion. Now look at water. Water can act as an acid and the water can act as a base. So we see here that the hydronium ion, water. So here we see the hydronium ion. Remember, acid is going to be anything that has lots of hydrogen ions. Okay, lots of hydrogen ions, and hydrogen ions on hydrogen is in front. So hydronium ion, H3O, 3 hydrogens, like a lot of hydrogen. So this is acting as an acid. Water with 1 extra hydrogen acting as an acid and +1 charge, hydronium. But the conjugate base is 1 less hydrogen ion. So the water is acting as a conjugate base of hydronium ion. So it's always conjugate acid-base pair is of what? Okay. Then comes the top ones are the strong acids. So keep this in mind. Strong acids have weak bases. So how do you know this? You see this arrow, red arrow going up. So the strong acids are written on the top. The direction of the arrow is pointing up. That means the strength is increasing. On the other hand, here you see diminishing strength on the top. So these are, the blue line is of the base. So the base is, the base, the strength of the base increases going top down. But here, the strength of the acid is increasing going from bottom to up. So top side, we have all the strong acids. Okay, but for the bases, the bottom side are the strong bases. The arrow is pointing down. So it's the opposite. So every acid will have every strong acid has a weak base. a strong acid will have a weak conjugate base, and a strong base has a weak conjugate acid. So here is a strongest base. OH ions are the strongest. Okay, OH ions are the strongest base, and their weak acid is water. So you see that dim colored water, like the red color is diminished. So lower. So the lower, so water it's not acid. Water is not acid. Water is not a base, but water can act as an acid and it can act as a base, right? So that's what it is. So water is, water, when you remove that one hydrogen ion, yeah, then it will produce only OH ions, and those are basic in nature, but OH ions are by nature very strong bases, okay? Now we have, same is the case here. So all these ones that are at the bottom, hydrogen phosphate, methylamine, bicarbonate, hydrocyanic, all these are very weak acids. So as you move up, the acids are strong. On the other hand, these bromide, chlorate, perchlorate, chloride, bisulfate, nitrate, all this sulfate, fluoride, acetate, all these are comparatively weak bases. So as you go down, you know, the phosphate and the hydroxide, these are strong bases, okay? So here's the thing. Now, we are going to now use this information, and we will apply this in determining the direction of the equilibrium. So I'm just letting you that this is a test. This is going to be on the test, like determine what is the direction of the equilibrium, which side is it, you know, going. So, all right, so this was on page 16, okay? So now, first of all here, write this formula, so that the direction of the equilibrium, so write this formula. Formula is direction of the equilibrium is from stronger. Now it's not strong, it's stronger. It's everything is in comparison. From stronger to the weaker side. You know, by nature, we go from the weaker to the stronger side. But what we are doing here, it's stronger because it has got hydrogen ions. So they are the ones that are giving away the hydrogen ions to the weaker. So the direction of the equilibrium is going to be from a stronger to the weaker side. So what you need to do is identify strong acid, strong base, and then, you know, just move the equilibrium towards the weaker side. Okay, so remember that products, whenever we are looking at the products, the reaction is moving forward, and forward is FWD. And if the direction of the equilibrium is towards the reactant side, then the reaction is moving backwards. Okay, so now let's look at this now. So these are some examples. Example. How to do this. Okay, so you have H2SO4. Okay, and it is reacting with water. H2SO4 is aqueous, water is a liquid. Okay, now you have to identify which side. Is it moving forward or is it moving backward, or what is the direction of the equilibrium? Okay, so this is the question mark here. Okay, which side is it moving? And then it's giving the hydronium ion H3O plus, which is aqueous, and this is the HSO4, 1 negative, and aqueous. Okay, so here's a step. These are the steps. Follow the steps. Follow these steps. Okay. One is that first, always it's easy to identify the acid. And as we talked about, that the hydrogen is written in front. So the other species, whether it's on the reactant side or product side, it doesn't matter. The other species, whether it's a reactant or product, I don't know, how do I write this? The other species becomes, or the other species is automatically the base, is base. Okay? Base can be hard to interpret because you know, it's a negative charge and sometimes it has a hydrogen ions and it can still act as a base, those things. So it's easy to identify the acid. So then whatever it's reacting next is the base. Next is every acid will have a conjugate base. So identify that. Identify the conjugate base. And identify the acid is a conjugate base. For the base, identify the conjugate acid. Okay, now using table 11.3. Using table 11.3, compare acid to conjugate acid and a base to conjugate base. Which one is stronger? Like compare the strengths, okay? The acid with a conjugate acid, excuse me, and a base to a conjugate base. Which one is strong? Okay, next is, once you have this base, conjugate base and the acid, identify which side is strong, which side is weak. Once you put the strength, so you just keep that the direction of the equilibrium is going to be the arrow. So direction of equilibrium is from the stronger side to the weaker side. Okay, so let's do this one first. Actually, I should move this out here so it's all in one place. Just give me 1 minute here. Okay, and this I just need to move this a little bit up. All right, and this comes down. All right, so this is the example, we will follow. Now H2SO4 and H2, so like we said, so the first H2SO4, sulfuric acid, commonly known. So this is the acid. If this is acting as the acid, then the water will be a base. Okay, that's one thing. Every acid, now this is H2SO4 is acting as an acid, then the conjugate base of H2SO4 is 1 hydrogen ion less, minus 1 hydrogen ion less. So this is HSO4, 1 negative. All right. Then we have H2O. H2O is acting as a base. All right. So if this is acting as a base, then H3O plus is the conjugate acid of H2O. So first identify that. So this is step one. Sorry, this is step one. One step, second step, third step. Now we are going to do the comparison. Compare, sorry, is it P-A-R-E? Compare H2SO4, H2SO4 with HSO4, 1 negative. Compare in table 11.3, H2SO4 with HSO4 and H2O with H3O plus. All right. Now, let's look at this, H2SO4 and HSO4. So here you have H2SO4. Clearly, you see H2SO4 is on the strong side. Now, look at the HSO4. HSO4 is on the, if sulfuric acid is on the strong side, right? Here's the strong side, on the stronger side, but the HSO4 is on the weaker, so weak base. Okay, so comparatively, HSO4 is weaker, but H2SO4 is stronger. So let's write this down here. So H2SO4 is on the stronger side, is on the stronger acid side, and HSO4, 1 negative, is on the weak base side. So that means this guy is stronger. H2SO4 is stronger. Okay. Now compare H2O with H3O plus. Okay. Okay. Now, since H2O, sorry, where did it go? Okay. Since H2O and H3O. Now, H3O, hydronium ion, and so here we have water is on both the sides. This is a weak. So remember, this is an acid. Oh, wait, one second. An acid. Did I even do this right? Oh, sorry about that. I made a mistake here. Give me 1 minute. I am so sorry. An acid with the conjugate acid. So that's what I was wondering. What am I doing here? Okay, sorry about that. Ooh, I'm so sorry. Hold on this. Just fix this whole thing again. Just occurred to me. H2SO4 is an acid. So you compare it with the conjugate acid H3O. Yeah, sorry about that, guys. Okay, compare from the table H2SO4 with H3O. That is the conjugate acid. Okay. Okay. And then the base is H2O, and compare that with HSO4, 1 negative. Okay. Now let's go with H2SO4 and H3O. Okay. Here we see, here we see H2SO4 is right here on the top. Sulfuric acid, H2SO, and then hydronium ion is at the bottom. That's what I mean. Okay, so here, if you look at it, the strength, the arrow is moving up. So hydronium ion is lower than H2SO4. So H2SO4 is stronger, is H2SO4. So let's put this in a different color. H2SO4 is higher than H3O. Okay, so this is higher, this is lower in comparison. Okay, so therefore on the table, placement on the table. Okay, placement on the table. Okay, next is H2O and HSO4. Now let's look at that one, H2O and HSO4. So here, H2O and HSO4. HSO4 is on the weaker and H2O is, moving towards the stronger side. So top to bottom. So HSO4 is weaker and H2O is stronger. So H2O stronger, and this is the HSO4 1 negative is lower, like weaker. Okay. And this is stronger. Okay. So we see that the HSO4, H2SO4 and the water are the strong ones. And in comparison, these guys are the weaker ones. So the strong ones, the direction of the equilibrium is going to be from the strong to the weak side, from the strong side to the weak side, the direction, the equilibrium. So in other words, the hydrogen ion, the flow of the hydrogen ions. So the direction of equilibrium is from stronger to weaker. Okay, so we see that in this case, the reaction is going to move forward. So let's just write this down, the whole thing. H2SO4 plus H2O more, it's still going to be at the equilibrium, but more moving towards this, the weaker side, which is H3O plus HSO4 1 negative. So this is stronger, both of them, and these guys are weaker, both of them. So this is basically giving away the proton transfer reaction. So forward. So when it's moving forward, this means that there are going to be more products in this reaction and comparatively less reactants. That's what it means. Okay, so more hydronium ions are going to be present. Less of the less reactants, more products, and the reaction is moving forward. So this, okay. So this is one thing. Okay, let's look at another example here. So this is one example, and I'm going to do another one. Example 1. Let's do another example. Example 2. Okay, let's look at this. Carbonate CO3 2- aqueous reacting with H2O liquid, and we're trying to find what is the direction of the equilibrium. Okay, and this is going to give you HCO3 1 negative, HCO3 1 negative aqueous plus OH 1 negative, okay, aqueous. All right, now we are trying to see what is the direction of the equilibrium. So same thing, you're going to first identify the acid, which one is the acid and which one is the base. So remember, we're just going to keep the guy that is neutral and has hydrogens in front will act as an acid. So which is the one here? We see water. So it's neutral, right? And has hydrogen in front. So that acting water, H2O is acting as an acid. Okay, H2O is acting as an acid. All right, so we identify the water obviously is the acid. So then the carbonate ions, the one that is reacting with it, is going to act as a base. That's one step. Second step is the conjugate acid and conjugate base. So H2O is acting as an acid, and this is going to give one hydrogen ion, and that gives you the OH ion. So remember that acid, and this is the conjugate base. Now, carbonate ion, CO3, 2 negatives, is going to accept, this was a base, right? Carbonate ion is a base. So this base is going to accept that one hydrogen ion, and it forms that HCO3, 1 negative charge. This is also 1 negative. So this is the conjugate acid of carbonate ion. This is the conjugate base of H2O. Okay, so we do identify that. Next is that then you're going to compare. Now this is a little bit, I also got confused last time. Okay, compare an acid to the conjugate acid. So in other words, we will compare water to water with carbonate ions. Okay, and base to the conjugate base. So here we have the base is the, wait 1 second. Again, did I mess up? Oh, God. Okay. Acid to the conjugate acid. Water to HCO3 minus 1. Okay, sorry about that. Okay, next is a base. Base is a carbonate ion, minus 2. And that gives you with, compare that with base to OH ions. OH ions, 1 negative. Okay, so this comparison has to be on table 11.3 table in handout. Okay, or from your book directly. Okay, so what do we see here? So water to bicarbonate. Let's look at this. So water and acid, and bicarbonate is a conjugate acid. So water and bicarbonate. Okay, water and bicarbonate. Let's see. Okay, here's the water down here, and bicarbonate is on the top. You see that in comparison, you see water is lower and bicarbonate is higher. Bicarbonate is moving high. Water is very, very low. So it means that water is very weak acid. Bicarbonate in comparison is a stronger acid than water. Okay, so let's write this down, that H2O is a very weaker acid. But which one was that? Bicarbonate, HCO3, 1 negative, is a stronger, in comparison only, is a stronger acid. Okay, in comparison. Now, on the other hand, let's compare the carbonate minus 2 to OH ions. Now let's go back and see carbonate ions and the OH ions. So here is, remember, top to bottom, OH is stronger. This negative, this is going this side, it's stronger, strength is increasing. So OH ions is the strongest anyways, but let's still look at a carbonate ion. In comparison, carbonate ions, if you see, look at here is the carbonate anion. Okay, so this carbonate anion is, oh dear. Okay, this carbonate anion is comparatively weaker base. So let's do this. So this is a weaker base, and this comparatively is a stronger base. So OH is stronger side. Now let's just go back and write this whole thing down. So so we are looking at this problem. Let me write this down here. The problem is carbonate, CO3 minus 2, aqueous, reacting with H2O as a liquid. This gives you HCO3, 1 negative, aqueous plus OH ions aqueous. Okay. All right. So carbonate. So we write this down. This is weaker. Water, we already looked at is weaker. So this is a weaker base. This is a weaker acid. And this side is a stronger conjugate acid and stronger conjugate base. Okay, so what is the direction of the equilibrium? The direction of the equilibrium is going to be moving backwards, more this side and a little bit this side. Okay, so that's the protons are going to transfer from the back to more products, so more reactants, less products. Did I put this here? Yeah, forward. So more products and less reactants. Here, more reactants, concentration, and the reaction is moving backwards. Okay, so that's how you will be determining this, like how many more, are there more products or less product? So that's the way to do this. Okay, let me just do one more, which is a study check problem. Study (11.4), and this is page 410. Page 410. Okay, here you're given the nitric acid HNO3 aqueous, okay, reacting with H2O. This is liquid. And we need to find what is the direction of the equilibrium, forward or backward. This gives you the hydronium ion, aqueous, and nitrate ion, NO3, 1 negative, aqueous. Okay, so now what does it contain more? Or what is the direction of the equilibrium? Or what does it contain more? Acid or like the products or the reactants? So here we are going to look at the nitric acid. As I said, nitric acid, strong acid. So this is a strong, or rather, it's always. So if one, identify the acid. So this is the stronger acid. Then it's reacting with something that is equally stronger base. I mean, water is not a base, but it's equally stronger. Okay, comparison. So if you identify the acid and you see oh, it's a strong acid, how do we know it's a strong acid? How do we know? And you look in this thing here and you look here, nitric acid is right there towards the strong acid side. So nitric acid, if nitric acid is strong, the other guy is also going to be strong. So that's something, just that's given. Okay, so the base is also going to be strong, in other words. Now, if that is strong, obviously these guys are going to be weaker. So this is also weaker. This is also weaker. The only difference now is the hydronium ion is coming from the water. So this is the conjugate base of H2O, and nitrate is coming from the nitric acid. So it's the conjugate, this is the conjugate acid of water, and this is the conjugate base of HNO3. Okay, all right. So that's the first thing you do. Identify the strong acids, strong base, and their conjugate acid bases. Next is you're going to do a comparison. Compare what? Compare HNO3 with H3O plus, and you compare H2O with NO3 minus. Okay, so table 11.3. Okay, in the handout, HNO3 and H3O. Oh, sorry, HNO3 and H3O. So you see HNO3 is stronger in comparison to the hydronium ion right here. HNO3 is on the top and hydronium ion is at the bottom. So we will put this here that HNO3 is stronger. This is comparatively weaker. Next is water and the nitrate ion. Same thing. You see this water and the nitrate ion. So water on the basic side. So nitrate ion and water. So you see in comparison, water is stronger on the moving top down. The top ones are weaker. As you move down, they're getting stronger bases. Okay, so here the nitrate ion is a weaker base than the water. Now you put this here. This is nitrate ion is weaker base than the water. So water in comparison is a stronger base. Okay, so these are the acidic side and these are the bases. So acid, acidic, and these guys are the basic. So I just don't want you to get scared with the water being acid or a base. You know, it's just acting, it's just acting. Now we see the rule. Now you are going to just put this here. I'm going to just write this equation back. Again, HNO3 aqueous plus H2O liquid and H3O plus aqueous and nitrate ion NO3 1 negative. Okay, this is plus 1, this is 1 negative aqueous. All right, so we said that this is strong. This guy is also strong. This is a strong acid. This is a strong base. This is comparatively weaker. Conjugate acid and conjugate base. So the direction of the equilibrium is from the strong to the weak side. Okay, weaker is going to a little bit go at the back. It's still equilibrium, but moving forward. So it is moving forward, and when it's moving forward, this side is still the reactants. This side is a product. So there are more products in this reaction. Okay, the reactants are less because the reaction is moving forward. And so the concentration of the products is more than the reactants. Okay, so this is something that you will be, you will be questioned on the exam. So just make sure that you guys practice this, okay? All right, now we are going to look at the next part, which is now we are looking at the next part, which is the dissociation constant of acids and bases. And then we will go from there, and then the values of the Ka value, okay? And then the for water, okay. Here is the, okay. Just a second. This is, I think, the first one. So I did a review. Yeah, proton transfer reaction, direction of the equilibrium. Also identify concentration of reactants or products. Okay, so these things. Okay, so we have now the next thing, which is part 2, which is dissociation constants of acids and bases. So dissociation constant of acids and bases. All right. So dissociation constant of acids and bases. So here we see the, how do you determine? Well, fine, we understand, okay, this is a strong acid, this is a strong base, that's fine. But how, like mathematically, how do you quantify? How do you get the, like, this is the amount of strength? How do you know that? So that is done, look at this. Let us say this is formic acid. Now, formic acid is the acid of, which is found in the ants. If you've ever been bitten by the ant, like how it pricks, it's like needles, right? Sharp needles. That's the shape of these molecules of formic acid. So the formula of the formic acid is HCOOH. And the way it looks like is this: C, double bond O, O and H. So it is this hydrogen, oh my God. This hydrogen is the acidic hydrogen, okay, because it is more attached to a polar bond. So not this one. This is non-acidic hydrogen. So let's write this down. This is acidic hydrogen. And this is non-acidic. So the one that is acidic is the one that is attached to the oxygen and it's a polar bond. So you can see that this one will already have a delta positive and oxygen has a delta negative, whereas the other one is not. It's covalently bonded to carbon. So this is acidic hydrogen always in polar bonds. And polar bonds are the OH bonds. Okay, always. Okay. So now what happens to this? So here is this formic acid. When it reacts, now this is aqueous, obviously, this is going to give the hydrogen ions. When it reacts with water, okay, and water is acting as a liquid and a solvent. Water is a solvent. It is dissolved in solvent, water, large amount. Okay, large amount. And this gives you, obviously, hydronium ion. So that hydrogen ion that is released, it attaches to the oxygen, gives the hydronium ion, and it gives you HCO2, 1 negative. Okay, and this is the formate anion. And this is the hydronium ion. Okay, so this is the situation with the formic acid. But how do we write this? How do we know what is the strength of this acid mathematically? So, obviously there are, machines. There is this one branch of chemistry. Okay, one branch of chemistry is the analytical chemistry. Another branch of chemistry is the physical chemistry. Physical chemistry studies the physical properties of substances. And analytical chemistry uses those machines, to determine those properties, measure those properties. Okay. So physical chemistry, the experiments are designed, and in analytical chemistry, those experiments are executed. Both of them have to work together. All right, so that's very interesting with chemistry. It's just such an amazing field. Anyways, so here we have this. We want to know what is the value mathematically, so we can measure it. So how do we do this? So obviously, since it is at equilibrium, you need to get the value of K equilibrium constant. Okay, so this is called the dissociation constant or the equilibrium constant of acid. And this is also called a dissociation constant of the equilibrium constant. So the equilibrium constant is written as, that's the expression, right? That is the product The products here are the hydronium ion and the formate ion, CH2O1 negative. So this is something you did in your previous class, chapter on equilibrium. Then comes the reactants, that is the formic acid and water, because formic acid is reacting with water, right? That's the expression of, that's how we write the equilibrium constants. But now, Ka is the dissociation constant of acid. So what is the difference between the two? The dissociation constant of acid ignores water. Okay, because water is in large excess. This is going to be, if you were to actually measure the concentration of water, it's going to be like a lot. But water is also a solvent. So this is the reason why it ignores it, because you don't need to bring it. Then it just disturbs the whole thing. So what do you do then? Then just bring in the hydronium ion concentration, H3O plus, so that you can just focus on how many hydronium ions are there, what the anion is formed, CH2O1 negative, over HCOOH concentration. Okay, so this is the dissociation constant of acid, Ka-W. Okay, now Ka has values. There are strong acids will have, just keep this in mind, because it's directly we are measuring the hydronium ions now. Acid, hydronium ions. And then of course the anion is just, and then whatever the acid is. So the larger, stronger acids will release lots of hydrogen ions. So weaker acids will release less hydrogen ions. That's one thing. So next is the strong acids. From this equation, as you can see, strong acids will have the value of Ka is going to be large. Weak acids, the Ka value is going to be small. Okay, now comes the question. If I give you two problems, now look at this examples here. I'm giving you HNO2 versus HF. The Ka value of HNO2 is, which is the nitrous acid, is 4.5 into 10 to the power -4. And the hydrofluoric acid is 3. The Ka value for the hydrofluoric acid is, Ka for HNO2, that's the nitric acid, nitrous acid, and HF is 3.5 into 10 to the power -4. So which one, I mean, both of them are weak acids, but in comparison, everything is relative in chemistry or science, basically. So which one is stronger acid? HNO2 or HF? Which one? So we look at it here. 10 to the power 4, 10 to the power -4, and 10 to the power -4, same. You rule out. So rule out 10 to the power negative 4. Now what are you left with? HNO2 and HF. HNO2 is 4.5 and HF is 3.5. So 4.5 is bigger than 3.5, right? So 4.5 into 10 to the power negative 4 is bigger than 3.5, okay, into 10 to the power negative 4. So the Ka of this is bigger than the Ka of this one. Ka of HNO2 is larger than the Ka of HF. So this is going to be stronger. Okay. Now let's look at another example. This is example 1. Let's look at another example, which is acetic acid CH3COOH versus H2CO3. Okay, H2CO3. So here we have acetic acid. Okay, acetic acid is the Ka value given is 1.8 into 10 to the power negative 5. 1.8 into 10 to the power negative 5. Carbonic acid is 4.3 into 10 to the power negative 7. Okay. Now, here we are going to leave this for us for a while, but now you focus on 10 to the power negative 5 versus 10 to the power negative 7. So compare. So 10 to the power negative 5 is bigger than 10 to the power negative 7. So this is a smaller number, and this is a bigger number. Remember, negative, bigger number. So negative exponents. Pay attention to that, negative exponents. Always, negative exponent, the one that is a smaller number is actually, if it's negative, it's a bigger number. Okay, so with that said, now we see that the 1.8 into 10 to the power negative 5 is bigger than 4.3 into 10 to the power negative 7. So that means the Ka of CH3COOH, acetic acid, is bigger than the carbonic acid. Okay, so this type of questions can be asked on the exam. The same thing applies for the bases also. The same thing applies for the bases. Same with bases. So, okay, here you have CH3NH2. Okay, anytime you have nitrogen, it's always going to be this basic in nature. So nitrogen makes the species, sorry. All right. So this is this guy reacting with water. So this is aqueous, water, liquid, okay? And, you know, at an equilibrium, CH3, NH3 plus aqueous plus OH minus. So this is in situ generation of hydronium ions, hydrogen ions, oh, sorry, OH ions, hydroxide ions. So that is why CH3NH2 is basic. Okay, so in this case, it is the Kb value. Okay, Kb is the equilibrium, the dissociation constant the dissociation constant for the bases. So dissociation constant for bases. Okay, so KB is equal to what? KB is equal to, here we are going to ignore H2O concentration because it is also acting as a solvent and is in very large amount. Okay, so that is why, same story. So here then we have the base, which is C. So let's put it in a different color. CH3NH2. Okay, and here you have CH3NH3 plus, concentration of this guy, and the concentration of OH ions. Okay, so that is the value of KB. And yeah, so basically the KB is, let's see if we have some examples here. We don't have for the bases, I don't have the examples here, but yeah, so anyways, you get, so it's the same thing, just like you have the acids dissociation constant, you will also be given the base, and the same math applies. Okay, now comes the next thing, the dissociation constant of water. Okay, now comes the dissociation constant of water. So just like the acids, dissociation constant of water. Okay, and this is also called the ion product of water. Okay, ion product of water. All right, so here the same thing, just like for the acids and bases we did, the same thing happens, but here's a very interesting thing. Okay, so here's your water. One molecule of water is like this, and it has the lone pairs. This is reacting with this other molecule of water. So the molecule of water is basically, they react to themselves. And this is happening all the time. So here's this water, oxygen, highly electronegative, delta negative charge. Hydrogen, delta positive. Hydrogen, delta positive. Oxygen, delta negative. And with that, we have these lone pairs, So what happens? This oxygen lends its lone pairs to this hydrogen, and this bond breaks. And when that happens, what is formed? We see that, but this is happening at an equilibrium. Okay, so here we see that hydrogen, so this hydrogen is not changing its position, this oxygen and this hydrogen, these guys are not changing the position, but a new bond is formed with the neighboring hydrogen. And now oxygen gets a full-fledged positive charge. Each of the hydrogens are still delta negative, delta positive, small charge. But oxygen, because it gave the lone pairs to the hydrogen, neighboring hydrogen, so now it has a negative charge. Plus, now it has released that OH ion. So now we have OH, and there is a negative charge on that. Okay, so OH is bearing the negative charge. So in reality, actually, the negative charge is on oxygen. Oxygen, because oxygen is electronegative, right? But we show it like OH. So in other words, you have H2O plus H2O giving you H3O plus and OH minus. So same story. water is also, H2O is also a solvent. Okay, so let's first write down the equilibrium equation. K equilibrium is equal to the product, the concentration of hydronium ion plus charge, concentration of OH ions, negative charge, over concentration of H2O and the concentration of H2O. So this is the equilibrium expression. Because water is also a solvent and has very large concentration. So ignore. But we can't just ignore things like that. Now we have KW. Okay, so now the equilibrium constant is what? This becomes the, give me 1 minute. Yeah. This becomes the concentration of H3O plus and OH minus. So this is the called the ion product of water. Okay, now what are the values here? So this is the value of KW is KW is equal to the hydronium ion concentration, H3O plus and OH ion concentration. And now we have here 1.0 into 10 to the power negative 14. Negative 14, okay, is equal to hydronium ion is 1.0 into 10 to the power negative 7. And the other one is 1.0 into 10 to the power negative 7. Okay, so what do we see here is that -7 and -7 multiply, but powers are added, it becomes -14. So that's the value of KW. The value of the hydronium ion and the OH ions is the same, 10 to the power negative 7 and 10 to the power negative 7, and is all added up to 10 to the power negative 14. So in other words, this means that for a neutral water, the concentration, in order for water to be neutral, concentration of hydronium ion, H3O plus, is equal to the concentration of OH ions. Okay, so their concentrations are the same. All right, now let's look at the concept of whether the reaction is acid, if the water is like, if there's an impurities in water, if they are, if the water is acidic, basic or so. So let's look at a study check. Study check 11.6, and that is on page 415. Now here we see I have a little dog in my house now. I purchased, no, not purchased, sorry. I rescued him. I got him from a shelter. So he's really adorable. Anyways, so what is the hydronium ion of an ammonia cleaning cell? What is the, so the question is, what is the hydronium ion concentration? So this is the language, okay? This double brackets, the concentration is expressed as these square brackets, okay? All right. Hydronium ion, what is the hydronium ion concentration of an ammonia cleaning solution with the OH ions, 1 negative. Okay. OH ions, the value given is 4.0 into 10 to the power negative 4. Negative 4. And I'm telling you this, there is going to be a question from on the test from these type of, test questions. Okay, so 11.6, page 415, 4.0 into 10 to the power 4 M. Okay, and OH ions. Okay, so here we have, you're given this. Now, write down the formula. And the formula is 1.0 into 10 to the power negative 14 is equal to the hydronium ion concentration times the OH ions concentration. All right. Now, we need to find so write down first what is given to you. So this is in the formula, negative 14 is equal to, we need to find the hydronium ion concentration, and we are given the OH ions, which is 4.0 into 10 to the power negative 4 M. Okay. So when you solve this, this becomes 1.0 into 10 to the power negative 14 divided by 4.0 into 10 to the power negative 4 is equal to the hydronium ion concentration. Okay, so how do you solve this? Mathematically, you can plug in the numbers on a scientific calculators and you can get the results. That's one piece. But if you do it manually, then first divide 1.0 with 4.0. Okay, that's first. So second, 10 to the power negative 14, okay, plus 4, okay? So in other words, let's just do this here, that 10 to the power negative 14 is actually dividing, 10 to the power negative 14 is actually dividing by 10 to the power negative 4. So in reality, that fraction is, that's what the fraction is. So I'm just kind of reviewing your, math skills. So when you bring this guy up, then it becomes positive. Negative becomes positive. So bring negative 4 from the denominator to numerator. Okay, so the arrow explains everything. So here this becomes 10 to the power negative 14 plus 4. Okay, so like I said, either use the scientific calculator or manually, this is how you will do it. From the fractions, solving the fraction. So let's do this. Oh, I don't have the calculator here, just a minute. Okay, so this is 0.25 and this one is 10 to the power negative 10. Okay, now you're going to combine these two. So the third step is combine 0.25 into 10 to the power negative 10. So that is just, but scientific notation what is the scientific notation here? Scientific notation is you are going to take this and put here. Move one place. And then this guy also changes. So one place, move one place. And here add 1. You moved one place. So this becomes 2.5 into 10 to the power negative 11. This is the concentration of hydronium ions. Okay, so I've tried to explain this. Now comes the question. Tell whether the solution is acidic, basic, or neutral. Now, keep this in mind, that tell whether acidic, basic, or neutral. Okay, tell whether acidic, basic, or neutral. Now, here's the thing, acidic, basic, or neutral. So acidic is, remember, 10, so if it is neutral, then it would be, 10 to the power 7. So here, the hydronium ion concentration, so there's something I forgot, I believe, to put it. Oh yeah, here. Something I forgot to put, sorry about that. Let's put this here. If you have, here. Okay. Zero, 7, and 14. So here, from here to here, from this side is the hydronium ion concentration, from 0 to 6.9. So that is the hydronium ion concentration. And from 7 to 14. And this is actually -7, sorry. This is, let's put it the other way around. Just give me 1 minute here. 10 to the power -7. This is 10 to the power 0. And this is 10 to the power -14. All right, so this is the hydronium ion, and that is the OH ions. Okay, so now based on this, we see that this is coming out to be 10 to the power more, more towards this side. This side is the basic side, and the other side is the acidic side. So this side is the acidic side. So let's write this down here. This is the basic, sorry. This is the basic side. Anything that is above, like 7, 10 to the power, like -8, and all the way till 14 would be basic. But from 10 to the power 0 to 10 to the power -6.9, acidic. So we see that the solution is so this is neutral. Okay. So in other words, neutral would mean when the hydronium ion concentration and the OH ion concentration are equal. Okay, so they'll cancel each other out. But since here we see it's 10 to the power 10 to the power -7 is above 10 to the power 10 to the power -11 is above 10 to the power -7. Therefore, the solution is basic. Okay, so this type of questions can be asked on the test. Tell whether it's acidic, tell whether it's basic, tell whether it's neutral. Okay, now next thing we are looking at is the 4. And here we are looking at is the pH scale, pH scale. So the same thing as we did above. So pH now, this concentration is now put on a scale, and that is a pH scale. When pH is less than 7, the solution is going to be acidic. Okay, the solution is acidic. And if the pH is equal to 7, then the solution is neutral. But if the pH is more than 7, then the solution is acidic. Neutral, the solution is basic. Okay, now here there's a formula for the pH, and the formula for the pH is, we are not doing the calculations because it's involving the log on the calculator, and I know it's hard for some students, so I'm not, I'm just canceling that out. But you should still know that pH, the formula, is negative log of hydrogen ion concentration or hydronium ion concentrations. Okay, pH is negative log of hydronium ion concentration. Another way of writing the hydronium ion concentration is equal to 1.0 into 10 to the power negative pH. Okay, 10 to the power negative pH. So these are the two formulas. So in other words, a very simple one, for example, and this is just an example for you to know, we are not doing the calculations, but just so you know. So pH is negative log of hydronium ion concentration. So if you are given, okay, let's say you are given a solution, H3O hydronium ion concentration is equal to 1.0 into 10 to the power negative 2 molar. So this is an example, okay, just so that's all knowledge base. Hydronium ion concentration 1.0, 10 to the power negative 2, okay, molar. So what is the pH? What is the pH for this? So remember that hydronium ion concentration is equal to 1.0 into 10 to the power negative pH. So therefore, the pH is equal to, you leave the negative, is equal to 2.00. Okay, 2.00. So just for now, just keep it like that. Okay, so we are leaving out the other pH related. Now, in my next video, I'm going to just do, because that's a stoichiometry, a little bit reactions. So in my next video, I'll just take a little break. Next video and notes is on the reactions of acids and bases. Reaction of acids and bases. All right, guys. All right. So I'm going to stop recording now. And if you guys have any questions, you can ask me, but I do hope that it was easy. All right. Okay. Take care, guys. Bye.